Picture a modern data center. It's a massive, climate-controlled warehouse humming with thousands of servers, and it is usually located hundreds of miles away from the people who actually run it. When one of those servers goes offline, a system administrator needs to fix it immediately. But driving across the country to plug a keyboard into that specific rack is rarely an option. They have to troubleshoot the machine remotely. In the early days of networking, administrators solved this by using a protocol called Telnet. It allowed them to send commands from their local computer directly to the remote server over the internet. Because physical access was impossible, managing this hardware required sending every keystroke, including administrative passwords, across the unsecured public internet. The fatal flaw of Telnet was that it transmitted all data in plain text. Nothing was hidden or scrambled during the journey. As this diagram shows, if a malicious actor managed to intercept the connection between the administrator and the server, they could read the usernames and passwords as they moved across the wire. To eliminate this vulnerability, engineers developed a secure replacement protocol, Secure Shell, or SSH. SSH protects remote infrastructure by forcing all administrative traffic through an encrypted cryptographic tunnel. Let's look at exactly what happens when an administrator sits down at a down laptop to fix a down server using SSH. The command starts with SSH, the username, and the server's IP. The laptop acts as the SSH client, making a request to the SSH server. The connection travels the internet, arriving at the server's default entry point, port 22. Because port 22 is a well-known target, administrators frequently modify the etc SSH SSHD config file to change this default port number and evade automated attacks. Executing this single line of code is the digital equivalent of crossing the globe to knock on a specific, guarded door. Once the server hears that knock, SSH begins completely encrypting the communication line between the client and the server. Unlike the plain text of Telnet, if an attacker intercepts an SSH packet now, the data is scrambled into mathematical ciphers. They cannot read the passwords or the commands. In production environments, administrators often skip passwords entirely in favor of a more secure method called SSH key authentication. A public key is stored on the target server, and a matching private key is held strictly by the client machine. When connecting, the server verifies the mathematical relationship between these two keys. If they match, the server grants access. This cryptographic handshake removes the risk of weak or stolen passwords while keeping malicious eavesdroppers locked out. With authentication successful, the administrator is now securely inside the remote machine. They can run commands and review system logs as if they were sitting in the data center themselves. This process scales to meet the demands of the entire global internet. Every day, administrators generate millions of these encrypted SSH tunnels to deploy applications and monitor infrastructure across AWS, Azure, and private clouds. AWS, or Amazon Web Services, and Azure are massive cloud computing platforms that host a huge portion of the internet. Because SSH is the primary way to interact with remote Linux systems, proficiency with the protocol is expected from anyone starting a career in Linux administration, DevOps, or cybersecurity. SSH provides the security layer that makes global, decentralized server management possible from a single laptop. If you found this breakdown helpful, subscribe to Linux for more tutorials on system administration and DevOps. Let me know in the comments, which Linux topic should we explain next?